Hi, how's it going today? Today I want to share with you a little video about the SCS curve number method. I got a couple questions about it recently, and for those of you who are trying to figure out how to calculate peak runoff or the volume of runoff for a site or a road or any piece of property or land, this is going to be a helpful tool for you. It's taken me a while to learn. When I was in school, I just didn't feel very practical. So I'm going to show you what I've learned over the last few years of digging into this and show you how to actually calculate it. Let's jump in. So I think you're probably all really familiar with the rational method, which is the simplest, most common way to calculate peak flow rate. Rational method is essentially Q equals CIA, where the Q here is flow rate in CFS, or cubic feet per second. We have the A for area, and that's typically given in acres. I is intensity, which is given in inches per hour. How intense or how fast is that water running off in inches per hour? So it's a speed factor, essentially. And then C is the catch-all to determine what site you have. If you have impervious, this is going to be a higher number. If you have forest or grass, this is going to be a lower number. So it's depicting how much water is going into the ground, or how much, I think it's called the coefficient of permeability. We'll just call it a coefficient. And this number typically ranges from 0.3 to 0.95. All right, just as an example, say we have a value of 0.8 for our C, got an intensity of 2 inches per hour, and we have an area of 2 acres. Simply, it's 2 times 2 times 0.8. There we go, 3.2 CFS is our answer, and that is just about as simple as it can get. So you can see why this is a very, very popular method for simple calculations. Is very fast. Now let's look at the SCS curve number. I guess, why would you ever use the SCS curve number if it's so stinking easy to use the rational method? Sometimes you have to use it, sometimes it's required. Look at the Clark County Stormwater Manual. You can see they're giving you different methods of calculating hydrologic. So here's an example from Clark County, Washington. Different methods are allowed for different types of design. So for example, the rational method, not applicable for runoff treatment, not applicable for flow control, and you can use it for conveyance. The SCS unit hydrograph, which is what we're going to be doing, or the SBUH, those two are come up with very similar results. They're sort of different ways to get to the same. I'm going to be showing you this one today. Applies to, so you can use it for runoff treatment, you can use it for flow control, for infiltration, or you can use it for conveyance. And then this other option is a specific requirement using the WWHM model that is really specifically for flow control, or you can use it for runoff treatment as well, and it doesn't work for conveyance. Now there's lots of software that can do this for you. I mean, HydroCAD, SSA, very easy ways to do it in that, but I want to show you how to actually calculate it by hand because it's good to understand how it actually works. So where do we even get the basis for our design? Like, where does this SCS even come from? And the document that I prefer to use the most is called TR55, which came out in 1986, so very, very old. TR55 is essentially a update to an older design methodology called TR20, which is where some of this stuff is defined, but I prefer looking at TR55. It's generally has easy formulas to follow. It's as easy as it's going to get if you're trying to determine peak flow rate using this methodology. So the first thing I'm going to do is I'm going to just go to this estimating runoff. Now from school, you probably all remember this formula. You've seen it before. You're like, oh, okay, this is what this is. This reminds me of what this is. What this formula is, this is the basis for determining how much water is running off your site based on how much rainfall you have. Now, one thing you got to note here is that the Q, when we're used to looking at Q equals CIA in the rational method, that's in a flow rate, or volume per time, cubic feet per second. Now this one is in inches, so this Q is not flow rate. So we're going to take this Q that we calculate in this with this step here, and we're going to then put this into another formula, which is then going to be used to calculate that peak flow rate. So just make sure you recognize this is not the same Q as the rational method. Very confusing, very easy to make that mistake. But you put in P for precipitation. P is initial abstraction. So we've taken this initial abstraction value, which is losses before runoff begins, versus the storage, the S here, storage, is while runoff is happening. So S and IA sort of combine into one term, and we're left with this formula here and this formula here, these two together. These two formulas are essentially added together, and we end up with this magic formula right here, with precipitation, which is our size of our storm event, curve number, those two values, we can determine what that runoff is. So this formula is a little bit convoluted to look at, but this is how this method works. So let's back up a tiny bit. Based on this formula, we really need to know rainfall, which this is very easy to look up, but curve number is something that we're going to need to calculate or figure out what it is. So let's figure out what is curve number. It's actually really similar to this value here, coefficient of permeability. It's a term that is going to help us determine how much water is running off your site compared to how much rainfall you're getting. And just like C, it's actually sort of in similar terms. So let me jump to the next slide here. So this curve number value is going to be, again, somewhere actually very similarly. Instead of being between 0 and 1, it's going to be between 0 and 100. Always ranges between 0 and 100. For a forest, you're going to have a curve number of about 40 to 60, I would say, depending on the type of forest you have. For a paved parking lot, impervious, we're going to have 98 is typically the value you use. So not quite 100% of the water runs off, but the vast majority. So once you figure out what your curve number is, and that value is going to be available in your program. It's also available in, as I was saying here, you got impervious, you're looking at 98. Open spaces are going to be anywhere between 40 and 90. This is lawn and grass. You can also break it down by urban district, industrial sites, residential sites. You can just use those values. And then if we want to look at woods or forests, you're going to be looking at the 30 to all the way up to 80. So there's a pretty big range here of what you want to use, but that's generally speaking, you want to figure out that term. Once you figure out that term, you can plug that in here, and then that is going to be, it's going to allow you to calculate that Q value. So I'm going to open up an Excel spreadsheet and just show you exactly how you would do this. So let's start with curve number. So S is going to be in inches. This is going to be the storage value, and then CN is going to be our curve number value. And so S is going to be equal to 1,000 over curve number minus 10. So if we have an 80 value for curve number, we got 2.5 for S. If we have a 98 value, we got a much smaller number, 0.2. And next, we want to punch in this value. So Q is, again, this is in inches, don't forget. P is also in inches. This is our rainfall event, so I'm going to just put in 4 inches to start here. IA is initial abstraction. S is storage. So these are all values in inches. And so IA value, let's just start right here. Typically this, and by typically I mean 99.99% of the time is going to be 0.2, so 20% of your storage value. So now we got to figure out what is our storage value. Well, we just calculated storage right here. So I'm going to set that equal to that. Now we know our initial abstraction. We know our storage. This was 80. These values change. And then Q is going to be equal to precipitation minus initial abstraction squared divided by precipitation minus initial abstraction plus storage. So I need to add another X. And 2.04. So you can see, really nice, helpful thing to do, take Q divided by P, and that is the percentage of water that's running off your site compared to how much it rains. So it rains 4 inches, 2.04 runs off your site, which is about 51%. If this was 98, that's 94% of the water runs off. So for a parking lot, you get about 94% with a 4-inch storm. If this changes to a 2-inch, a little bit less, 1-inch storm, a little bit less, 0.5-inch storm, a little bit less. Just keep it as a 4-inch storm, which is a pretty typical 100-year storm event in the Pacific Northwest. So you can play around these values and just see that. Now, this is also available in HydroCAD. You open up a project. So let's look at this value. I have area of 2, curve number, let's set this to 80, and I'll keep my time concentration to 18. I'm not going to be looking at that value just yet. First thing I'm going to be looking at is, I got a 3.9 in storm, so let me change. Actually, I'll just change it right here, 3.9. So you can see 3.9 inches, runoff, 1.96. That's all I did, was I calculated how much volume of runoff is going to run off my site compared to how much rainfall came onto my site. Now the next thing we want to calculate is this 0.76 CFS. How did they calculate that? So that is going to be a totally different formula. Once we figure out what that Q is, we can now punch that into a different equation, which is this one right here. Okay, so look at this formula. Q peak. This is the same rational method Q that we were looking at before. Q and CF. This is Q peak in CFS. Now here's a new term. We need to figure out what this is. Unit peak discharge. We have our area, and this time it's in miles, square miles instead of acres. We need to make sure we get the right units. And then there's the Q volume, Q, that runoff inches that we just calculated right there. And then this is a pond and swamp factor that is almost always equal to 1, but in oddball situations can be different. So we know this one right here, Q. This one's going to be 1. This one is relatively easy to calculate. We just got to convert from acres or square feet to square miles. And then QU is now going to be the one that we need to calculate here. So how do we calculate this QU term, and what is it? Well, again, QU term is sort of another term, sort of like the coefficient of permeability. It takes into account time of concentration and several other factors. These change based on the size of the storm event. These also change on the type of storm event, and then they help you calculate a new term. So a lot of different stuff going on in this equation. You can see why software is very helpful to figure it out. But I'm going to show you how to do that. So let's look at that. So now we're going to be looking at Q peak in CFS, QU, AM, square miles, Q in inches, FP, which is just normal. I'm going to just set this as 1. Here's my area in miles. I'm going to have this equal to, so I'm going to cheat a little bit. First, I'm going to have area in acres, so I can more easily type this in. I'll make this 2. I'll make this equal to 2 divided by 640. I need a few more significant figures so I can actually see what this number is. So divided by 640, that converts acres to square miles. I'm going to need to calculate my QU, and my Q peak is going to be equal to QU times mile squared times this value, which is my Q in inch, times my flood factor. Q in inches is going to be equal to 1.96 that we calculated before. Again, if I change this number, that will change. So I'll keep it at 80 for now. Okay, so here's the tricky part. How do we calculate this value? You can see it is a mess, right? So I'm going to call this log QU is going to be equal to C log time of concentration. And then I'm actually going to move this down one, call this C2. Okay, there we go. And then I'll set this as time of concentration, and this will be equal to log this. So I think in our example, we had set this time of concentration to 18 minutes. And you got to notice here, the time of concentration is in hours for this. So there's just a lot of conversions going on. I'm going to set this one for minutes. Time of concentration now 18 minutes equals 18 divided by 60. And this is actually going to be equal to that. So now we have a negative value for our log TC. So what next? How do we calculate these coefficients? Where do they come from? TR55, there is magic table depending on rainfall type. So Pacific Northwest, we're in type 1A. Most of the country is in type 2. So let me just pull this up real quick. So you can see here is the US, type 1A is Pacific Northwest. Most of the country is type 2, which is everything that doesn't have a shaded around it. So type 1, type 1A are a lower peak related to the volume. Everywhere else is a higher peak related to the volume. Now maybe I want to show you a really helpful little tool here. Within HydroCAD, you can come in to this value, and if you click on rainfall, view storm, I'm going to change this to intensity. So here's my type 1A value. Here's my type 2 value, so you can see these are the same amount of rainfall is happening, 4-inch storm or a 2-inch storm, but that top point is the peak runoff. So you can see a 4-inch storm is going to have way more peak runoff in a type 2 event than it is in a type 1A. That means more flood-like events are happening, even though Texas gets 35 inches of rain in Houston area, and Portland, Oregon gets 35 inches. A 4-inch rain event in Portland and a 4-inch rain in Texas are not the same. They're much different intensity. So I'm going to be looking at these values here, and let's just pull those in. So in this example, I also need to calculate a value called IA over P. And so depending on your different IA over P value between 0.1 to 0.5, that's going to tell you which coefficient to use. So let's put another value in here, IA over P. And I know my IA is this divided by, so 0.12. I'm pretty close to that 0.10. So it's not exactly right, so I really would need to interpolate between those two values. But for this very crude example, and I'll show you how to set up a little bit more exact, but this very crude example, I'm going to set this, but I'm actually going to change this value to come up with piggyback my answer a little bit. 3.9, C81, 84. Here we go. If I set this to 84 for my curve number, now I have an IA of exactly 0.1. And that gives me a value of CO, C1, and C2. So 2.03250, negative 0.31583, negative 0.13748. Okay, there you go. Now log Q, U, is going to be equal to, let's go back to that equation, equals this plus C1 times log TC plus C2 times this squared. So I got my log QU value. Now my QU is going to be equal to 10, the inverse log of this 144.56. All of that was to calculate the right value to put into my peak discharge equation, which I'm also showing you right here. So now, in our example, we've got 144.5. Our Q value was 2.28 equal to 1, and this value in miles squared is 0.0313. And that gives us a Q of 1.03 CFS. Let's see if that gives us the correct value that we're expecting. So let me jump into HydroCAD and see what HydroCAD gives us. Now if we do our SBUH, gives us 0.94. So we're a little bit higher than that. Now if we change this to SCS, we're at 1.8. So we're sort of right between. Honestly, we should be really similar to this. We're a little bit off, and I think there's even more calculations that go into this in HydroCAD, but generally speaking, we're right in the same ballpark. And so, yeah, that's what you come up with for doing it using the TR55 methodology. All right, so the next step, I would say, if you want to actually use this for calculating stuff, which I don't know who would want to versus how much easier it is to do in the software, but next step would be, as your IAP changes, we really would need to interpolate between these values. We're actually, I guess in this case, we are below 0.1, so we'd want to use these exact values. But what if this curve number changed to 80? Now we want to be somewhere between 0.1 and 0.2. So what I did is I took all these values, copied them into a spreadsheet form, and I'm going to put them right here. And so this is my formula way of doing this. And I said, so equals, if this value is less than or equal to 0.1, then I want to have it be equal to that. And you can see it's not less than 0. But if it was, like we had 84, it turns into 2.03. So instead of it being, if it's false, now I want it to be if less than or equal to 0.2, and I didn't do that correctly. If this is less than or equal to 0.2, then I want it to be, I want to forecast known X is that, known Y's are these two, and known X's these two. And so you can see it gives me 2.07, which that is, yeah, between these two values, which is sort of like what you'd expect. And now again, if this was 75, this is now 0.12, that works pretty well. Now if this is 65, you can see this is 0.27. Actually, I'm even above this next value. I'd really want to be 0.68 or so to be between 0.2 and 0.25. So I do another one. If that one's true, if that one's false, I'm going to do if B16 is less than or equal to J7, which is this value right here. Then I want it to forecast this value. Now these would be my known Y, and these would be my known X's. Okay, there we go. Pretty well set up for these values. Now if I drag this down for C1, I screwed up my value, so I'm going to have to add some of those little dollar signs in that we love so much. B16 should always be dollar signed, and then this H7, I would want a dollar sign, I7 I want a dollar sign, and J7 I want a dollar sign, and then also want a dollar sign the forecasting value H7 and I7, as well as N and J7. Okay, let's see what happens. I missed a value. See this value right here, B17. I need to fix that one. So okay, and one other one got screwed up. Let's see what that one is. B16 right here. Okay, so this should work for all three of these. Again, I didn't actually put it in for every single one, so I need to add a couple more if functions with the forecast, just like I did here. But if, as long as I'm not getting really low with my curve number, which I don't really that often, I think 66, 67 is my, anything 68 and above, this formula works for now. And I'll just copy formulas over, really. So Copy that, and I'm gonna copy that over, and same with that one. Okay, so let's see how that works. Go back to my, I think it was 84. I'm now at 1.03. Let's just try another value, 98. This is impervious. What do we get in HydroCAD for this value? Let's change this to 8. And again, we are in SCS 1.77, so not exactly the same, but also a little bit higher, just like we previously. SBUH 1.57, so it's right between those two values. So if you wanted to be a little bit conservative and try to come up with the exact same value, maybe you could multiply this by 5% higher or something. If you're trying to come up with the same value, it looks like I'm even a little bit higher than that, 7% higher, call it. Another thing you can play around with is curve number. So say we're at 5 minutes for curve number now, because now we have impervious surface, 1.86. Let's change this curve number to, or change the time of concentration excuse me, to 5 minutes. Now we're at 2 CFS. See, maybe our 7% increase hurt us a little bit. So, but yeah, that's how you do this methodology. It's pretty annoying to do it for each different equation, but I'll just show you the potential of why you might want to know this methodology. So, I like programs, but I much prefer spreadsheets. So here's a spreadsheet that I've set up. This is in my, if I want to do conveyance for a project, instead of having to run all these things in a program, I can just say, okay, I got, how many acres do I got? I got 1 acre at 84 curve number, that's 8. And it gives me, with a very convoluted forecast, which I'm showing you what I did previously, it will calculate the flow rate in the SCS methodology. And that's for a 4.3 inch storm. If I want to do a 2 inch storm, now it changes down to 0.2 CFS, and vice versa. So you get the point of why this could be valuable. So one last thing I wanted to do was compare some of these values, the rational method, because that's the alternative in a lot of cases. Why would you use this value versus the rational method? So let's just compare them side by side. So rational method, and here is the SCS curve method. So here are some C values for the rational method. Let's look at a couple examples. So we'll do one for single family of the type C soil, and then we'll do one for a paved street. I guess it doesn't really matter, 0.95. So 0.5 for single family residential type C soil. Let's just compare those. C residential, and then we'll just do paved street. Okay, so we'll just stick with our, I guess this is where it really comes down to what storm event are you looking at. So I'm going to do a 10-year storm. I'll do it. 10-year storm for both of these. 10-year intensity 2.18. It's a pretty standard one to use in the state of Washington. So 2.18 for a 10-year, 2 acres. Sounds pretty good. What did we decide this was? 0.15. 0.5. Again, the ease with which you can calculate this is amazing. That can't be right. That sounds right. 0.5 times 2 is 1, so 2 point. All right, now those values will be the same. Now this is going to be 0.95. So it's probably going to be about double, because 0.95 times 2.18 times 2. 4. Okay, now let's look at the equivalent values. So a 10-year storm is about 3.3 inches of precipitation, 2 acres. For residential, I'm going to call this 15-minute time of concentration. Sounds about right. And so that gives me a peak curve number value. Let's see, this is probably going to be, check our cheat sheet. Residential type C soil, call that, I'll just call it 83. 83-ish. 85 gives us a peak flow rate, and I should probably highlight this because it's a little bit harder to see. 0.84. So how does that compare? Definitely lower. 0.8. So it's about half of the value. And then our paved scenario would be 98, and for time of concentration, call this 5 minutes. I'm going to call this 1.57. Does that seem right? That does seem about right. So again, you're getting much lower flow rates with this. So big picture, what I would say is you're trying to be conservative. Rational method in terms of pipe sizing, inlet sizing is going to be a big deal. Another way you could work around this is maybe you're going to use, instead of a 3-inch storm for 10-year, maybe you're going to design your SCS methods for a 100-year event, so you can increase the volume or the flow rate, still lower than the equivalent rational method. But just remember, rational method typically more conservative. It doesn't have to be. Again, it's all based on what your intensity value that you're putting in is. So someone's determined that this 2.18 inches is the correct intensity, but the equivalent for SCS would actually be more like 1 inch per hour. All right, well, I got into the weeds there. I'm really hoping that this was helpful for some of you who are really looking forward to calculating some of this stuff by hand or with a spreadsheet. And yeah, thanks so much for checking out my stuff, and I hope you have a great day. Feel free to leave any comments below if you have any questions. It doesn't make sense to you. Thanks very much. Bye-bye.